Private license.
Where's the camera? There. You have to look there at the camera. Okay, good. So we can start. So we have, it's an honor today to have Vasia, Vasiliki from Boston University, who is leading what's the name of the group?
CASP.
CASP, which stands for?
Complex Analytics and Scalable Processing.
Scalable Processing. So Vasia's group works on streaming technologies, right? Privacy preserving, computing, databases, data stream processing, and more recently also serverless computing, I would say, right? So there is a big, I would say, interest overlap with our group as well. And as many of you know, me and Vasia, we are among the few people that started the Apache Flink project, right? Among the first creators. So Vasia focused on the graph streaming project when she was a PhD student at KTH, while I was working on the streaming framework. And we exchanged a lot of ideas. And now here we are again at KTH. And today, Vasia is going to present their recent work, actually the last 3 years. It's
almost
3 years or 4 years of work on the applications of cryptography on relational databases and decentralized data processing, right? So this is a very important field, and only a few understand this because we don't have cryptography experts everywhere, especially in the computer science community. It's a very tough application, basically, to understand the cryptography semantics and also apply them to preserve privacy in complex computations, right? So I'll give the mic to you, Vasia, to present.
Thanks, Harry.
And maybe we can take the questions in the end.
No.
Or?
Let's make this informal and interactive.
Okay.
Just stop me when
So you can stop, but don't overdo it.
It's okay. Even if we don't make it till the end, I think it's fine.
Okay.
Right? So I have a bunch of content, but the idea is to understand what is going on. So if this is new to people and they see it for the first time, feel free to stop me because
it's not so many people, so it's
sure.
okay.
Yeah, exactly. And then you cannot follow the rest if you don't understand the basics anyway. So
I will put the speaker high enough, so if someone from the online audience has a question, we can hear you from the speakers, right?
Okay, excellent. All right, so thanks, Barry. It's great to be back after so many years. Actually, I was here last year as well for a few days, but as Barry said, I started here at KTH, so I did my master's and PhD, part of my master's and part of my PhD. In fact, here, and since 2020, I've been at Boston University, so I have a pretty young group. This is us. This is my group as of today. Maybe a couple of people are missing. This is our new shiny building. We're very proud of it. And as Barry said, we work on different aspects of data-intensive systems, right? So we are a systems group. We're not a cryptography group, but we want to investigate how we can use our knowledge about how systems are architected to make complex computations practical, right? And by complex computations, I mean different things, but we currently focus on 3 areas, so stream processing and microservice applications, graph machine learning applications, and privacy-preserving collaborative analytics, which is the topic of today's talk. Okay, great. So I will start by motivating, what kinds of applications we're looking at and why they are important, right? So what do I mean by secure collaborative analytics, right? So consider a set of data owners, right? People who have sensitive data, like healthcare providers, companies, or even end users like us. And they either have private data that they cannot share with others, or sensitive data, or data that are that give them a competitive advantage, for example, proprietary data, right, like companies. And even though this data is private and they cannot share it either because of legal concerns or business concerns, they do share a common interest. So it would be to their benefit if they can somehow put all of their data together, right, and run an analysis on the union of their data. For example, healthcare providers might be interested in running a large-scale disease surveillance study or understanding the effectiveness of a drug, and the more data they have, the better the analysis, right? Similarly, companies, and this is a real world use case that the city of Boston has been deploying for a few years now, I think since 2017. So companies might agree to share their employer, to contribute their employee salary data for understanding the gender or racial wage gap, but only if we give them a guarantee that nobody will learn anything about the employee salary data, right? So they are interested in understanding, is there a gap? But in order to agree to contribute to the study, we need to give them some guarantee that their data will be protected, right? Or users like us, I know, we're very used to sharing our data with all kinds of companies for recommendations, right? We don't even think about it. But, what if we actually cared about our privacy? Can we still get all the, advertising and recommendations that we get today, like all these, good features that we are interested in, right? So these are the types of use cases I'm targeting. Okay, so multiple data owners, shared common interest, they want to analyze the union of their data. And just to clarify exactly what I'm looking to protect here, we know how to protect data at rest, right? So we know how to store data like in the cloud and protect, for example, this data from any adversary or even the cloud providers, right? For example, there is a AES standard, right? So we can encrypt the data, it's there, it's at rest, nobody touches it, it's protected. We also know how to protect data in transit, right? When we communicate between two or more entities, right? For example, TLS. What I'm looking at here is to protect data in use, right? So I want to protect data while it is being analyzed, okay? So my goal is to be able to compute exact results on secret inputs. I want to compute a query on data that I cannot see, essentially, okay? So how can we protect data in use? That's the question here. There are various techniques, and I'm not a privacy expert, but I am familiar with some of them, so I can discuss some alternatives if you want to later. But for this talk specifically, I'm going to focus on a family of cryptographic protocols that we call secure multi-party computation, okay? So what is secure multi-party computation? It is a family of cryptographic protocols that allows mutually distrusting parties, right, to perform any kind of computation on private data, on their private data, while providing guarantees that the data will be hidden from the untrusted parties and from any external entity, all right? And I know this sounds like magic, but it's not, it's math, right? It's cryptography. And the key idea is that I'm not going to trust any single entity. I'm actually going to distribute my trust, all right? And then there is an assumption here that the parties don't trust each other, but also they don't cooperate to reconstruct the input, right? So we have this non-colluding assumption, right, that they have different interests and they don't have any interest in actually colluding to reconstruct the data, right? Because in this case, they will reveal their own. Okay, so that's the assumption under which I'm working on. Good. So there are many, many protocols, right? And with MPC, you can basically have any number of parties. You can protect against external adversaries. So not just those participating in the computation, but also external people who might want to learn what is happening, right? There are different levels of security and different threat models that these protocols can operate under. Some of them are called semi-honest. So semi-honest, I will not go into details, but just for you to understand, semi-honest means that we trust that the parties will actually follow the protocol. They will try to learn what they can from what data they have and what they can observe, but they will not cheat. They will not try to deviate from the protocol. Okay, so they will follow the protocol and they will try to reconstruct with whatever information they get from that protocol, right? Malicious means that we also protect from parties that deviate from the protocol on purpose. So they might not follow exactly the steps of the computation. They might try to do something like malicious in order to extract information from the other parties. Okay, and there are protocols that protect for both of these cases with different, of course, like performance. Implications. We can execute arbitrary computations on MPC. And I hope you will agree with me, MPC is, at least some protocols are easy to explain. There's a high-level idea, right? But the challenge I'm focusing on is how to make it practical. So it will become clear very soon, I hope, that this is a computation that has overheads. Some of them are hard to overcome, and this is exactly what we are focusing on, right? How to make it faster, more efficient, and practical for real-world use. Okay. So what I'm going to do now is I'm going to give a brief introduction to MPC using one specific protocol that I think is easy to explain. And it's the first protocol that I also understood when I started working on this, right? And it's the first protocol that we implemented in the system I'm going to show, okay? But this is just an example, okay? So the protocol I will introduce is called, is based on replicated secret sharing. So what do I mean with this? Again, we have our data owners, right? Hospitals, companies, users, right? And I can have any number of those data owners. And they have private data, right? What I'm going to do is I'm going to have each data owner encode each and every data item they have, right, using one of two techniques, either arithmetic sharing or Boolean secret sharing. So arithmetic sharing means that every data owner will take its data item that I assume for now it's an integer, okay, and it will generate two random integers, actually three random integers, so that if I add them up modulo 2 to the k, where k is the length of the integer representation, I'm going to reconstruct the original data item. All right, so in practice, you generate two random numbers, two random integers, like uniformly at random, and then the third one you get by subtracting from the raw, like the plain text data. All right. Similarly, you can do Boolean sharing, which is you take the string, the bit representation of the data value, and then you generate two random bit strings so that the three of them, if you XOR them, they give you the original item, right? The original bit string, okay? And then I'm gonna have each data owner send two out of these three random shares to one of three, to each of three computing parties. Okay, so I have any number of data owners, three computing parties. These are the ones that will actually follow the protocol, right? And you can see that now each party only has two pieces of the puzzle, right? So on their own, they cannot reconstruct X. Okay, none of them. Only if they collude, they will be able to reconstruct X, all right? So for this particular protocol, I have the guarantee that, as long as a majority, 2 out of 3, are following the protocol and they're semi-honest and they don't try to cheat and collude, then nobody will learn anything about the original data. Okay? Make sense? Good. So let's see how we can use this now to actually, compute something. the very first thing I'm going to show you is a simple addition. All right? I have two data owners, arithmetic secret sharing, and I want to compute S plus T. Okay? Just the addition. Data owner A has S. Let's say this is number 5. It creates the secret shares. And data owner B does the same. They each send 2 out of 3 shares to the 3 computing parties, right? And it is, I think, easy to see that each computing party, all they need to do is just add their local shares, right? And if they add their local shares, they are going to end up with 2 secret shares of the result of the addition, okay? So now every party has 2 random numbers, right, that represent a share of their result. Okay, so they don't know what they computed. They know they computed an addition, but they don't know on what input data they computed the addition, and they don't know what is the result of the addition. Yeah? So I can do another addition on top of this, right? So you can see how I can compose now operations. Yes? Okay, let's do something a little bit more advanced and see how we can compute multiplication. Okay, again, every party has 2 out of 3 shares. And what they want to compute is S times T. Okay? If I rearrange the multiplication formula, you will see that each party can again use their local shares to compute one of these terms that I call their M1, M2, M3, right? So party 1 can compute this term. Party 2 can compute this term, party 2, party 3, right? And if I add these 3, then I get the result of the multiplication, right? So this is just a simple rearrangement. I'm going to have them do that, right? And now they each end up with 1 share of the result, okay? If I want to now do another multiplication on top of this or another addition, what I'm going to need to do is have each party send the second share, right, to the corresponding party in this ring, okay? So then if I do that, then each party will have 2 out of 3, and now I can again do another addition or another multiplication, right? Great. And now, since I have addition and multiplication, in theory, I can compute anything, right? So that is the basic, these are the basic 2 operations. And we have the corresponding logical AND and XOR operations if I use Boolean sharing instead of arithmetic. Okay? Any questions so far? We're good. Okay, excellent. So what we have been doing for the past 4 years at BU is we have been building what we now call the BU Secure Data Analytics Stack. So we want to use MPC, right, so that we can enable users to easily run relational analytics, time series analytics, and also machine learning, maybe analytics in the future, on top of these like very basic primitives, okay? So given the MPC protocol functionalities that I showed you, addition, multiplication, division, XOR, logical AND, and different types of protocols, right? So depending on the protocol, this computation I showed you is slightly different, right? But they all have these like primitive operations. We have built on top higher level primitives for equality, for example, compare and swap, converting from one sharing to the other, square root, and so on. And on top of these higher level primitives, we have been building libraries for analytics, right? So I've built a library for relational analytics where the user can write a SQL query, and that query will be compiled to oblivious primitives, which we'll call the basic secure primitives, right? We have built a library for time series analytics, right, where you can do time-based operations, again, compiled down to MPC primitives, and we are working on doing some simple ML computations as well, right? So I'm going to focus on the first two, which are work that we have published already, secrecy and TVA, right? And there is quite a lot of work that we're doing on the parallel and distributed runtime, right? So how do we make these computations practical, as I said before, right? And, to give you an idea of how difficult this problem is or how slow these computations are, right? So just think about the protocol that I showed you, which is one of the actually very efficient ones, right? Every multiplication only needs one round of communication, right? And now, keep in mind that these parties, in order to be non-colluding, they are probably communicating over the internet, right? They're not in the same data center, like, because they are separate entities, right? You have maybe 2 hospitals or 3 cloud providers in our case, right? Different cloud providers, right? So this round of communication is actually quite expensive, right? So it's not a cheap thing to do. And if every single multiplication requires 1 round of communication, right? Imagine a SQL query, right? So when we started like four years ago looking at this problem, it kind of seemed impossible, right? We're looking at papers who reported MPC computations on a few thousands of records, or that it would take hours to run an aggregation, or that it takes an astronomical amount of time to run something under MPC, right? So we, started thinking, can we do something better, basically, right? Can we improve on this, or is it a dead end? Maybe we can, we give up on MPC and we don't use it, right?
Is the slowdown there like times 43,000 times slower?
Yeah, so this is the slowdown compared to plain text.
Okay.
Right? Which I think, yeah, it gives you an idea of the overhead, right? But if you could do this on plain text, you wouldn't do it secretly, right? Okay, so, this is a problem that has concerned people before us, for sure, right? I mean, there are people who have been looking at this problem for quite some time, and many, interesting and smart ideas have been proposed. But what we saw is that most people were trying to leverage a trade-off between security and performance, which is something, probably natural to do. It's like, can I leak a little bit of information in order to have a gain in performance, right? And there are 2 types of trade-offs, roughly. One is information leakage. So maybe instead of leaking data, I could at least leak access patterns. And if I leak access patterns, then the compiler might do something smarter, right? Or I can leak the size of intermediate results. And if I know the size of intermediate results, then maybe my optimizer can do something smarter, right? And there is a big line of work in this area. And the other type of trade-off that people have been trying to exploit is hybrid execution, right? So what if I have the data owners also be the computing parties, and then they do part of the computation locally on their own data, and then I only do the global aggregation under MPC, for example, right? So there are these 2 directions. But when we started talking to our collaborators who actually wanted to use this, we understood that for some use cases, any kind of leakage is actually completely out of the table, right? And also, many of the people who want to use MPC don't know how to set it up. So it's very hard to have a data owner also be a computing party. Like the hospital IT departments, they don't have this kind of expertise, right? So first of all, why is information leakage such a, can be problematic, right? Let's just consider this example. I have the wage gap study that I showed you before, right? And in this wage gap study, I have a set of queries that I want to run, right? And let's say that this is one subquery, right? At some point, I want to find all employees who are women, managers, and have a salary above some value, right? If I allow just the size of this intermediate result to be leaked to the computing party, right? They can possibly identify the company where this is coming from, or even the employee, right? Because how many women managers are there with such a high salary, right? So these kinds of problems arise when you leak intermediate data sizes. And when you leak access patterns, you can also infer information about the original data. So let's say in the same study, I had a conditional like this one, like what if person one salary greater than person two salary, then gap, right? If I allow the computing party to actually observe how many times this conditional is true, so how many times I take the branch, right? Then they can possibly infer which of the companies, which of the data owners is contributing to the gap more than the others, right? And that is an issue, all right? So in order to avoid any kind of leakage, I need another ingredient to combine with MPC, which is oblivious computation, right? So I want to make sure that any kind of computation that these computing parties perform is completely, entirely data independent. So no matter what is the data distribution of the input, they always perform the same sequence of actions, okay? So I cannot have data access patterns that depend on the actual shares, on the values. I cannot have any conditionals in my code. And I cannot reduce at any point in my query the intermediate data size, because this will potentially leak information, right? And of course, now you're thinking, okay, that's even worse than before. I had the communication issue, and now I cannot even, get rid of any data. Like I cannot reduce them, right? But it is what it is. So how does it work then? If I cannot have if then else. You have a question?
So, but we get this problem only assuming that we want to leak access patterns, or
we don't want to leak them. Yes.
Yeah, but assuming we would use like a protocol that might leak access patterns, then we use oblivious computation in that case. But
yes,
the previous case of we do super expensive communication and so on, that still works without oblivious computation.
Yes, so any primitive that I build on top of those, like equality, for example, if I want to use equality or inequality, right? I still need to make sure that I don't leak any access patterns, right? Yeah, the additional multiplication I showed you, they don't leak anything, right? But then the idea is how do I compose those to implement higher level primitives that also don't leak any patterns or intermediate results, right?
Yeah. All right.
So if let's say I cannot say if A is less than B, right? I cannot just compute I cannot subtract them and then do greater than 0, for example, right? How do I compute A greater than B in a data independent way? That's the question here, right? And essentially, what we do is convert every kind of computation or higher level primitive into a formula, right? That will give us the result, the secret share of the result, right? So here I want to compute A greater than B. And what I want is a result phi that is a secret share that either tells me 0 or 1. Like 1 if this is true, 0 if it is not true, right? And how can I compute this? This is a kind of naive protocol, but the core idea of what we have implemented is actually the same. If I had 2 3-bit numbers, like A and B, what I'm going to do to make this data independent is actually go bit by bit and compare them and say, if the most significant bits are not the same, then A is greater than bit when A2 is set, right? And then go and do the next bit comparison, and then the next bit comparison, until I find the first bit where they differ, right? And then, but I cannot stop. I have to scan the entire.
Always go through the same pattern.
Exactly.
Even if you know the result.
Exactly. Exactly.
That's the point.
Right. So this is how we do oblivious computation. And now I said multiplication takes one round, right? So does logical AND. So here each one of these ANDs are one round of communication between the parties, which, however, I can batch when they are independent, right? So if I have a data representation of k bits, of length k, then each one of these inequalities requires log k communication rounds under MPC, right? It's a tree. Yeah? Great. Now if I have this like higher level primitive, so I know how to compute A greater than B and I get a 0-1 shared, I can also implement a relational operator for selection, right? So if I had the table, employee salary, and I want to compute, is the salary greater than some value, right? What this corresponds to is adding a new column to my table, right? Where this column is this phi value, secret shared, right? But as I said before, I cannot just get rid of these two columns, right? Because then I am revealing how many of the employees actually have a salary greater than 3,000, right? So instead, I'm gonna like carry around these 0 and 1s and I can use them in later computations. Okay? Great.
So you have to materialize more.
Yes, so first of all, you cannot get rid of rows, right? Unless you have a limit. This is the only operator that lets you get rid of rows. And every time you compute like a selection or distinct or group by, that corresponds to adding a column, right? With a 0 or 1. For example, if I wanted to do a group by here, I would have a column that has a secret share where the group starts, right? Everything in between would be like zeros or garbage data. And then I would have like a special value at the beginning of each group. And then you can use this information to do aggregations, for example, on top of that, right? Or if I had another selection here, right, then I need to compute a logical AND on the two columns to get the conjunction of the selections, right? If I had salary greater than 3,000 and some other filter condition, right, then it's basically logical operations on these secret bits, okay? Great. Okay, so given now that you know where all this like complexity and performance overhead comes from, the question we started asking is, can we actually achieve practical performance, right, without compromising on the security, without any leakage, and without demanding of the data owners to use their own resources, right? So we want to use the cloud. We want to use the outsourced setting. Sure, the answer is yes. I'm not going to show a lot of performance numbers, but this is just one highlight from the secrecy paper where, we started from a few rows and we can actually run complex queries on millions of rows in just a few seconds, right?
That's good.
So, and this is also the single-threaded, like very basic implementation where we have much better numbers now, but yes, we managed.
But
Yes,
what
I'll
is
tell you
the
how.
computational complexity of that?
Here, so this is a query that has
Let's do what happens if it grows.
if it grows more.
Yeah, exactly.
So for this particular query, because it only has, I think it has many filter conditions, but not group by join, it will scale to much, much larger. I think now,
scale.
yes, it can scale. The difficult computations that we're working on now are group by operations, which are still fine because it's just a logarithmic number of rounds you can do. Joins are the most expensive, right? Of course, because you can imagine in the worst case, if you know nothing about the input data, you have to compute cross product, right? And then if you have a query with multiple joins, like a multi-way join, then that doesn't scale at all, right? But if you have some sort of foreign key primary key relationship, or you know something about the input data, then you can do much better. I can tell you in the end about it. It's what we're working on now.
Okay, great.
But it's promising. So for this first work for secrecy, what we focused on is one, amortized network I/O, right? And we saw really big gains by simply batching those messages, right? So understanding which of those messages are independent, and then reducing the amount of communication rounds by doing vectorized execution. So instead of running each one of these selections one by one, right, we have primitives that operate on vectors or entire tables, right? And then you can batch all the communication. And then we worked on reducing the MPC costs. So we implemented a query planner for relational queries that, instead of looking at the size of intermediate data, which doesn't give you any information for MPC, instead it looks at operation costs, so number of MPC operations, synchronization costs, the rounds, and composition cost, right? So if I have, let's say, multiple selections and I have to compose these columns, and then we apply logical, physical, and protocol-specific optimizations using a cost model that is based on these MPC-specific costs, right? That's the main idea. And I'm just going to show you a couple of highlights. The paper has a lot of such optimizations, right? So the first one is very simple, very effective, just message batching, right? So what we looked at before, I have a table with various values and one column where I want to compute an equality or inequality on, right? So each one of these inequalities requires log k communication rounds, right? It's what I showed you before, that formula, right? But I don't need to run them one after the other, right? These are completely independent, right? So instead of running them in a sequence, I can batch them, right, into large messages, right? And then I can have secrecy compute the inequalities on the entire table in log k plus 1 rounds, right? And this gave us orders of magnitude already performance improvements. This is one example, right, where the red is eager, so just
That's
sending small messages, and the green is batched. And this is LAN. In one, it's the gap is even bigger. So we implemented all of the primitives in secrecy in a batched way. All of them are vectorized. Great. But then we started looking at more interesting optimizations that we could do. And we started wondering, okay, we have decades of experience with query optimization, doing reorderings, right, to optimize query performance. Do any of those reorderings that we're aware of apply here, right? And I guess the most maybe common reordering you do in a query optimizer is pushing down a filter, right? So let's say we have a query, a plan like this one, I have a join and a filter. Any plain text optimizer would actually push this filter down, right? So that the join can be applied on smaller data, exactly. But under MPC, this does not actually improve joins performance at all, right? Because I cannot get rid of the rows, right? So then we were wondering, okay, is this true for any kind of reordering? Is there still something we can do, right? And yes, we found a few cases where reordering still works, but most of these cases are not common for plain text optimizers. So they're still valid algebraic transformations. It's the same relational algebra that we use here to find the alternative plans. It's just different types of plans that have lower cost under MPC. Yeah. Here's one example. We have a select distinct and a join, okay? And let's say both tables have the same size, and if I execute this plan, the original plan, assuming that my distinct is implemented with a sort-based protocol, I need n square log square n operations and messages, and log square n rounds, and n square space, because I need to materialize the output of the join, and then compute distinct on top. Okay? But here, I can actually transform this plan to this equivalent one, pushing the distinct down. Okay? And in this case, I can actually reduce both the operations, not asymptotically, but still reduce both the operations, the number of rounds, but most importantly, I don't need to materialize the output of the join anymore. Okay? Because I can compute distinct and then pipeline the result of the join. It's my last operator, right? It's not a blocking operator anymore because there are no other operation after it. Okay? So what I end up with this reordering is log square and fewer operations, messages, which in practice makes a huge difference, right? Because the larger n, the larger the benefit.
Excuse me, when you say log square, you mean log log or what?
No, yeah, log square.
Log
n.
Oh, okay.
Yeah.
Log log. It's not log n square. No.
Yeah.
But the distinct is applied at the combination of, the joint result, right? So
In the original plan.
But then you push down the filter. Or
You push down the distinct.
Because the distinct requires the join input, right?
It's a distinct on the join key. That's why you can do this here. Yeah. So if you look at the here, right? So it's the same attribute.
Okay, so you filter out the duplicates.
Yes, early. You don't actually filter them out, right? You add this column.
Yeah, I
the
understand.
distinct adds
exactly.
a column that says, okay, this is a distinct value, this is a distinct value, right? And then you can compute join on that.
That's smart.
Yeah.
And since the join, since it's the last operation, then it doesn't need to
materialize.
Okay, so
exactly. You can do it in a pipelined way. That's what you.
So we are allowed to then output only a smaller result set.
No, you output everything. You just don't need to store it at once.
Okay.
Right? You don't need to store it and then apply another operation on top of it. You still output the entire result.
Okay.
Yeah. In general, we have some high-level guidance and rules in the paper. So we came up with some examples, but I think we have not exhaustively found all the different reorderings you can do. But we found that, for instance, it always pays off if you can push down sorting. So do the sorting as early as possible, which is, it's an expensive operation. And since you never reduce the size of intermediate results, the fewer data you sort, the better.
Because
right?
also the join has different implementations, right? So if you have a sort merge based join.
Yes, so that's the thing, right? Here, if you know nothing about the inputs, you cannot do any smart.
Optimize.
You cannot do any smart type of join. You can only do cross product.
Cross product and then filter and then
yes.
select. I see.
Yes. We are now looking at different types of joins.
But if you somehow hide the properties and optimize.
Hide what?
I don't know, which of the two data sources has a larger file, for example.
So that you already know.
That you know.
Yes.
But then you can do, for example, broadcast hash join based on the size of these sources.
But then you are going to
reveal that.
You're going to reveal access patterns if you do hash join.
So that's impossible to avoid.
It's not entirely impossible. It depends. So if you can have if your query bounds the output size, then you can use that to do something smarter. So most of the cases we're looking at now, and I think that's reasonable, right? You never just output the result of a join, right? You usually do an aggregation on the result of a join, right? And if that aggregation bounds the result size, then you can use this information to also bound the intermediate result sizes, and then you're not actually revealing anything to the any computing party, right?
Let me ask a general question.
Yeah.
About revealing access pattern. Did you classify which access patterns are really dangerous and which are not? Because you might be able to reveal some access pattern, but
I think you might. No, we're not doing that at the moment. We're hiding everything.
Hiding, yeah.
Yeah. But I'm sure someone has done this kind of work.
Exactly,
yeah. And there are also works that try to hide like this intermediate information by adding like differential privacy noise. Like, so you don't reveal the actual result sizes, but you reveal noisy result sizes, for instance. And then,
exactly, but because
you could do
that
this
is you can do. You can combine with differential privacy.
Yeah, the
when
problem,
you are communicating.
it gets a little bit complicated afterwards to guarantee security, like to combine the different techniques and have like a clear threat model, right?
Exactly. I see.
Because here now, nobody will learn anything about the input or the result sizes, and it's a clear like threat model. But if you start adding, like revealing a little bit, then it's hard to infer what or prove in the end what can you reconstruct about the input. But yeah, definitely you can do any of this. All right, I am taking this slowly. All right, so yeah, many more details in the paper. I'm not going to show any other optimizations, but we have physical optimizations as well, like operator fusion, for instance, protocol-specific optimizations, like doing smart things with the arithmetic and Boolean sharing or going from one to the other. Lots of proofs if you're into that, and multi-cloud experiments on queries, on complex queries, right? Also aggregations and joins. Okay. So that was secrecy about relational analytics. Right, and then we also looked at time series analytics, which come up a lot in the health domain, right? So these are types of time-based aggregations, right, on data that have timestamps, right? And we wanted to see, like, can we combine essentially all the relational operators we had with these like time-based operations, like can we compute windows? Right? So I'm only going to show you one example because, again, there is a lot to show here. But essentially here we looked at different types of windows. One of them we call the gap session window that essentially detects in a time series periods of activity followed by periods of inactivity, right? So let's say I have a time series of a movement, like from human subjects, right? And I want to compute some aggregation during periods when they are active versus periods when they are not active. For example, what is the heart rate of patients who are administered a specific type of drug when they are walking, running, moving versus when they're sleeping, right? These kinds of analysis I want to do here, right? And essentially, what I need to do now is under MPC, right? Because the timestamps are sensitive here, I need to protect them, right? Under MPC, detect these windows, right? And then apply an aggregation on top. Okay. So how could I do this? First of all, let's understand what the problem is and look at the naive protocol, right? So let's say this is my time series, my table. I have a timestamp column and some value. Let's say this is like just coordinates, okay? And for simplicity, here I have it sorted by timestamp, but it doesn't have to be. Like we'll sort under MPC, but I'm not going to show how sorting works, okay? And keep in mind that I don't actually have the values, right? I have secret shares, okay? So I have like data that looks random, but I know one of them is a timestamp and the other is the value, okay? What I want to compute, again, is a column, right? That in this case is the window ID, okay? So I want to compute under MVC this column where the first three values belong to the same window, right? So my gap is 3, right? So this is the same session, this is another session, and this is another session, okay? And then if I have the window IDs, I could do group by aggregation, whatever I want, all right? But I'm looking for a protocol that can produce this column, yeah? Okay, so how can I do this? I mean, a straightforward way of doing this would be to sequentially scan all of my rows, right? And do this inequality protocol that I showed you before, right? So does this row belong to the same window as the previous one? And then once I have the result for this, I can do the same, like row by row, right? Anyway, I'm gonna have to access each row once, right?
And ask if it is greater than 3 or not.
Exactly. So that doesn't sound like a very bad protocol, no? Except that because these inequalities are not independent, I actually need n communication rounds. If I need, or ON communication rounds, right? So remember, each one of those is log K, right? And then I need the result of the previous row in order to compute the result of the current row, right? So I'm gonna end up doing n communication rounds, which is terrible, right? So instead of this naive secure sessionization, we came up with another protocol, a more efficient protocol, that works in 2 stages. So the idea is the following. Instead of trying to compute the final column directly, we're gonna first compute the inequalities independently across overlapping neighboring rows, right? So we're going to compare the gap between consecutive events, right? If they're sorted, that is going to give me at least like how far apart are the consecutive events, right? So I'm computing this delta, and this I can do in log K, right? So this has constant. Because these are independent, they can be performed in parallel, okay? These inequalities.
Like pairwise comparisons, right?
Yes, so
you can have
overlapping though. So 1 with 2, 2 with 3, 3 with 7, and all of these I can do in parallel.
Exactly.
Yeah, and I get this column first, right? How far, where are my gaps, right? And then I compute, is this distance greater than the
What I
gap?
don't get, so is this allowed? Because if you do log...
This is not log n, this is constant, this is log K.
Log K is what?
K is the length of my bit representation.
Okay,
so it doesn't depend on the number of rows,
right.
right? That's what I'm trying to avoid.
Right, yeah.
Right, so no matter what the size of the table is, this is log K. I can do them all in parallel. Yeah?
No, I get it.
So, and then I can compute the next column is delta greater than gap, again with a bulk of inequalities, right? And what I have now is the start of my windows, right? I have a session starting here, a session starting here, and a session starting here, right? And then all I need to do now is figure out whether the intermediate rows belong to the window above or the window below, right? Because now I know where my boundaries are, okay? And for this computation, we use, I have the window starts, and then I assign the actual window ID there, and -1 or special value to all the unassigned rows. And now in order to figure out whether the intermediate rows belong to the window before or the window after, we follow a protocol that is called butterfly style network. So essentially, what I'm going to do, I showed you this already, is start and doing comparisons at increasing distances. So first I'm going to go and compare at distance 1, then at distance 2, then at distance 4, then at distance 8, right? And instead of doing a sequential scan over all the rows and n communication rounds, I'm only going to need log n, right? So at each one of these steps, of the computation at each one of these levels, I'm computing this inequality, this conditional. So if window ID is unassigned, then assign this row the window ID of the previous one. And because I'm going distance 1 for 2, 4, I know that the one before will be assigned already. Yeah? So how do I do this without the conditional? We use a technique that is fairly well-known, the oblivious multiplexer, right? So again, I'm gonna turn this into a formula, right? That says a bit and the value, XOR not bit and the value, and the other value, sorry, right? So it's, I assign one or the other with this oblivious multiplexer. Okay, and then distance 2, distance 4, and all of my rows are now assigned, right? So I end up with log n rounds instead of n, right? And this is much, much better. So using this protocol and similar protocols for the other windows, we implemented like a library of secure time series analytics. And we have experiments in the paper where we show how we can analyze both offline time series, so really, really large time series data, and also online scenarios where you have a deadline for your window. So you have to compute a window before the next one arrives, right, on millions of participants, essentially. Okay, great. So relational analytics, time series analytics, I showed you.
Quick
yes,
question
of course.
about the windowing still.
Yeah.
What if there's like an adversarial case of we only have one window, maybe, because there's never a gap this month?
That's fine, then all of the rows will belong to the same window.
Yes, but in that case, we'll have still like n rounds of propagating this, no?
No. The same protocol works in that case too.
Oh yeah.
We'll show one window.
Yeah, you make exponential steps.
Yeah,
Okay,
like all of them will be assigned to the window above.
Right. Yes. Okay.
Right?
Yeah.
Because at every layer you assign further and further away.
And you
and
don't.
Then you have these overlaps.
Yes. Okay,
and all the middle ones will eventually be assigned to the right one.
Mm-hmm.
Yeah.
Thanks. Yeah. Thanks.
Great. Okay, so the third component of this work is actually making these computations practical for the cloud setting, right? So I showed you some optimizations, how do we make them faster, right? But why do we care about the cloud? I mentioned before that we don't want to assume that the data owners have private infrastructure or expertise, because they don't. And also the cloud is a good choice because a small number of third parties, let's say 2 or 3 cloud providers, can actually support a large number of data owners. Because peer-to-peer MPC, where the data owner is also a computing party, doesn't scale with the number of data owners. So the more parties you have, the more expensive the protocol, right? So we want to keep the number of parties small. And also we hope that cloud providers will benefit from this, and they will start offering MPC as a service. Actually, what I'm going to show you next relies on the data owners actually providing this as a service at some point, right? So that you can say, I want to use Amazon and Google Cloud as parties for my computation. Okay, so we wanted to show that this is possible, right? So we had the demo at SIGMOD this year where we prototyped this deployment, this like automatic deployment of MPC computations. We call this query shield. So we have a data analyst and a data owner. And the data analyst, what they do is they use a web client and they create an analysis. So they will register like a description and say, I want to run this query. This is the data I'm looking for. This is the threat model, and I want to use these cloud providers, right? So this looks like this a little bit. So the data owner says, I'm looking for this table of data. I want to run this semi-honest on AWS, Azure, and Google Cloud, right? And this is the query, right? So the query is always public in MPC. right? And then once this analysis is in the system, our backend creates buckets for the secret shares on the different cloud providers. And then the data owners can look at this catalog and say, okay, I have data for this computation, I want to participate, right? And then they can upload data to the buckets, right? So our service sends them pre-signed bucket URLs. So these are write-only pre-signed URLs for private buckets that only the data owners have access to, right? And they compute the shares and write them to those buckets, right? So again, 2 out of 3 on each one of them. And from the point of view of the data owner, like they don't actually need to do anything complicated. They can either enter data like manually or upload the CSV, right? And the secret sharing happens at the browser, this like random data generation, right? So they send those. The analyst then receives a notification that, okay, you have data owners who want to participate. So then the data analyst can start the analysis, right? So if that happens, then our backend will provision VMs in the different clouds. So generate the computing parties. The computing parties will follow the protocol, right, to compute the analysis. They will write the result shares to buckets that only the analyst has access to, right? And then the analyst will receive the shares of the results and do the reconstruction again locally in their browser. Okay, so they're gonna see the analysis, the results of the analysis. Okay. Again, we have more, the details about this in the paper, but essentially, this is what I meant, that we hope the cloud providers will offer this as a service. You can see now that this prototype we have is not secure, right? Because we have the backend, our application, creating all the parties, which means we have access to all of the data, right? Ideally, what you want is for these parties to be provisioned by the cloud provider, right? So the cloud provider gives you this service, right? And not a single entity has access to all of these accounts. Yeah? Great. All right. So we're working on a bunch of challenges next, but essentially our view is that we're going to have to rethink the entire stack if we want to make this work. So I showed you some optimizations that focus on the query engine, the protocols like decisionization, and the communication, right? But we are working on how this software interacts with the hardware as well. We are working on parallelizing the runtime so that we can do these computations with multiple threads. And we are also like really working on user interfaces so that we can make this accessible to people who don't have the expertise, right? So our current ongoing work is about plugging in different protocols. So with the same stack, you can do like relational analytics, time series, whatever we add on top, targeting different protocol backends with different security guarantees, looking at parallelism, optimizing more complex queries with multi-way joins, right? And hardware acceleration. So can we get any benefits from using GPUs, FPGAs, or any other modern hardware? This is the team, the secrecy team. 3 PhD students and 3 faculty members is the core team. And then several bachelor, master's contributors, 1 high school student.
High school?
Yes. She built the interface
Okay.
that I showed before, yeah. And yeah, we have partners and support from industry and NSF. And all of our papers are open access, and all of our code is also open source.
Thank you.
Use it, try it out. That's it. Thank you.
Thank you. I guess we asked most of the questions here, but maybe people online have more. I'm not sure. Now it's the time to ask.
So I have a question. Can you hear me?
Yes.
Yes.
Fantastic. Yeah, cool work. I very much like it. So two questions. I'm wondering about, so in my domain, I work a lot with strings instead of intervals and integers that you showed. So can you comment on support for string operations?
Strings.
Yes.
Yeah. As long as we can map them to a fixed length representation, then we can apply operations on them. We haven't actually done this, but yeah, it should be possible. It's going to be more expensive than doing it on integers. But yeah, you're going to have to assume like a maximum representation length, and then you can do operations on strings as you do on integers.
Okay, fantastic. And maybe the second question is not much related, but are you around this week for a chat?
I'm around until Friday.
Okay, then I'll.
Yeah, it's my last week here.
In
But
Chester, right?
I'm around like in.
And now,
yeah.
now we're at main campus. So today, for example, is one possible day.
Yeah, but I can also come like another day if you want to. And we can always chat on Zoom as well.
Okay, fantastic. Thank you.
Thanks. Other questions?
Who else? Any more questions? If not, we can also you can also mail Vasia. You have your mail here, right?
Yeah, absolutely.
Get in touch. So thanks again. I think it's time to wrap up.
Thank you.
And thanks everyone.
Very nice work. I mean, the whole project.